Have you ever noticed something strange while walking at night? The moon seems to follow you. You walk down the street, and the moon stays beside you in the sky. Turn onto another road, and it appears there again. Even if you travel for kilometers, it still seems to move with you. But other things behave very differently. Streetlights slide past. Trees drift behind you. Buildings slowly disappear from view. Everything nearby clearly changes position as you move, except the moon. It remains almost fixed in the sky. Nearby objects move, yet the moon seems to stay with you. So this raises an interesting question. Why does the moon appear to follow you when you walk? To answer that question, we need to look at how our eyes interpret motion and distance. When we move through the world, our brains constantly compare objects around us. Nearby objects shift position quickly. Distant objects shift more slowly. You can notice this easily when looking out of a train window. A fence beside the tracks races past almost instantly, but distant hills drift slowly across the horizon. Both the fence and the hills are standing still. The difference is distance. Objects close to you change their apparent position much more when you move. Objects far away change much less. This effect is called parallax. Parallax simply means that an object appears to change position when the observer moves. Nearby objects shift a lot. Distant objects shift only slightly. But the moon behaves differently, and the reason lies in just how far away it really is. A helpful way to understand this phenomenon is to imagine the world as having two layers: a foreground, which contains nearby objects, and a background, which contains extremely distant ones. You can think of the moon as part of that distant background, almost like a light painted on the sky. When you move, objects in the foreground shift position dramatically. Objects in the background barely appear to move. Your brain constantly compares these two layers to understand motion. Imagine walking along a road at night. As you move forward, nearby street lamps slide past you quickly. Even objects a few hundred meters away shift noticeably. But something much farther away behaves differently. The moon. The moon is about 384,000 kilometers from Earth. That distance is so enormous that even walking several kilometers barely changes your viewing direction to it. To see why this happens, we need one more simple idea. This idea is called angular position. Angular position simply means the direction an object appears in the sky from where you are standing. If an object is extremely far away, small movements by the observer barely change that direction. So when you walk, the direction to nearby objects changes quickly. But the direction to the moon changes almost not at all. Your brain compares these changes automatically. Nearby objects move. The moon stays almost fixed. And when something remains steady while everything else moves, it begins to feel as if it is moving with you. This illusion reveals something interesting about how we perceive motion. Our sense of movement does not come from a single object. It comes from comparing many objects at different distances. Nearby objects provide strong motion cues. Extremely distant objects provide stable reference points. And the moon, because it is so far away, naturally becomes one of those references. This effect is not unique to the moon. Distant mountains can sometimes appear to follow you while driving through a wide valley. The same principle is at work. Because those mountains are so far away, your movement barely changes the angle from which you see them. The moon simply exaggerates this effect. Astronomers actually use this same principle to measure distances in space. As Earth moves around the Sun, nearby stars shift slightly against the background of more distant stars. By measuring that tiny shift, scientists can calculate how far away those stars are. This method is called stellar parallax. So the simple illusion you notice while walking at night is connected to one of the tools astronomers use to measure the universe. So the reason this happens is surprisingly simple. When you move, nearby objects shift position quickly in your field of view. Distant objects shift more slowly. Extremely distant objects appear almost fixed. The moon sits so far away that its direction in the sky barely changes as you walk or drive. Your brain compares the rapidly moving foreground with the nearly motionless background. Against the motion of nearby trees, buildings, and streetlights, the moon appears steady. And that steady position creates the impression that it is traveling with you. The next time you notice the moon accompanying you along a quiet road at night, the scene may look exactly the same as always. The moon will still seem to follow you, but you will know that nothing in the sky is actually moving with you. What you are seeing is simply the result of distance and the way our minds interpret motion in the world around us.